Questions?
Joel, is there any explanation how this law might come occur?
Yes.
Let's say a foundation,
Yes.
these power laws, which is a different issue, because there's not a variance and so on included. They have some explanations why they came about, and maybe you have also here, or Taylor has an explanation.
Taylor did not give any explanations,
But
but
you-
have you heard of a branching process? Okay. There are formulas for the means and variances of a branching process. And a critical branching process is one where the expected number of offspring is exactly 1. But if you look at the and Taylor's law does not hold for a critical branching process, but it holds for all non-critical branching processes, growing and declining exponentially. And you can prove, and I have proved, that Taylor's law holds for all branching processes that are not critical, with an exponent of 2 for supercritical and 1 for subcritical. And there's a discontinuity, a singularity in the exponent when the process passes from super to subcritical. So that's one example. The second example is linear birth and death process, a standard stochastic process model. You can prove that Taylor's law holds in the non-critical case. There are Markov chain models. There are multiplicative random walk models. I'm giving a specialist's answer to a specialist. Excuse me, if you don't know what those models are, it doesn't matter. But there are many mathematical models that lead to Taylor's law, and that is an interesting theoretical area of research.
Any more questions?
Brian.
So just to try to understand a bit more what the Taylor's law implies. So you mentioned that you might think of it as clustering. And
That's
so,
one interpretation, yes.
okay, so I'm thinking, so, because for example, we're involved now in doing spatial projections.
Good.
And so thinking about an application to these and understanding what would it be testing? Is the idea that you might take the gridded data, historical data, or projections, that it would give you a sense of the clustering of population density spatially and how that clustering might change as population grows in some area? Is that the basic idea?
Suppose you had a gridded population and you had some historical information about that population's distribution over time. Let's say, suppose you could look at the means and variances at several points in the past. Suppose you had 5 points. Then you can fit a straight line to those log means and log variances. And now you have a set of alternative spatial projections for the future. You do the same thing for the future, and you ask yourself the question, first of all, do my future projections agree with Taylor's law as well as my historical observations? Secondly, I have a parameter estimate for the history, the intercept and slope. How well does each of my alternative future projections agree in intercept and slope? If I have a history that goes like this and a projection that goes like that, then I'm suspicious. At least it seems less plausible than one that continues the same trend, at least in the short term.
And since the law is a relation between two variables,
Mean and variance.
yeah, you might have multiple projections which are in equally good agreement, even though they have, say, one's growing fast, one's growing slow.
Absolutely right. And in the example that we gave, we had 6 projections. 2 of them turned out to be the best. So then we examined those 2, and we found out what did they have in common and what did they differ in. They differed in fertility and mortality, what they had in common was internal migration and external immigration. So what was driving the differences was the level of migration. We didn't know that without having done these calculations. So you might learn something about what's influential in these projections. And those two projections were the ones that turned out to agree most closely with the actual data from 2011 to 2015. So in that instance, this method got the right answer.
Nico?
Thank you, Joel, for a very interesting talk. My question is about inertia in the population. You had population at several consecutive years.
Yes.
Now, from one year to the other, the mean across counties in Norway, or the variance across counties in Norway, when it comes to population size, doesn't change much. And what Taylor's laws say, or your application to population says, is that they move in tandem, the mean and the variance.
Yes.
This is not very surprising after I've heard you, after I thought about it, because of the inertia in the population. Have you ever tried to apply or check Taylor's law for population increase? Year on year population increases, which are much more volatile.
I have not done that, and it's a very interesting idea. And if somebody would like to work on that, I'd be very pleased to collaborate. We have the data to do it.
Yes.
We can do it.
And I think because of the auto-regression in the population development, after I heard you talk, it's not very surprising that they are so regular.
Yeah. But I have a model of the Norwegian situation, which is the simplest model I could think of, namely an exponential growth model for each county separately and individually. And that model does a pretty good job. And so it's consistent with your saying that there is very substantial momentum. But we haven't looked empirically at the increments. And that's a good question, and I don't know the answer.
Have you tried applying this to the countries of the world?
I would like to do that. Would you like to do it?
Quite possibly, yes.
Good. But I mean, I'm happy to either observe or to pitch in. But yeah, it's an obvious thing to do. I don't know why nobody's done it.
One more question? No more questions. Thank you, Joe.
Thanks to you. Congratulations, Wolfgang.